So I'm changing topic to basically an easier topic. So I'm going to talk about the Duval singularities. So you can find, if you go to my website, plus surfaces, you'll find a little text called duval.txt, which is here. And you know, it's not completely written and so on, but it's basically what I'm going to talk about, and something that I would eventually like to finish as a chapter of a book. So let me. You can start this from several different points of view. So let me start from the simplest point of view, which is I'm going to take. So a surface. Now this is a surface X in, C3, A3, with locally with an equation that is locally, analytically, x squared plus y squared plus z squared. Right. So this is ordinary double point. Or node. Or it's also called an A1 singularity. Right? And so, what do I have to do to resolve it? So the resolution is the same thing as the blow-up. And so, the picture is, I take, so that's this picture. I take a new surface here that looks sort of like this. And inside there's an exceptional curve. And this exceptional curve now is E isomorphic to P1, which is the tangent cone, Px. So it's this P1, it's this P1 that goes around there, and E squared is minus 2. Right. So I had this kind of picture earlier in the lecture course where I said this is a way of producing examples of curves with self-intersection minus 2. What do we have to, in equations, to do the blow-up? I take f is x squared plus y squared plus z squared. Here's my, it's contained in C3. Let me just say C3. If you want to work over a funny field or something, then you can do A3. You can easily modify the argument. So let me take a map from C3 to C3 here, where I'm thinking of writing x equals x1z, y equals y1z, and z equals z. Right, so this is C3 with coordinates x1, y1, z. And this is C3 with coordinates x, y, z. And the map there is defined like this. Right? The map is defined by x maps to x1 times z, y maps to y1, z. It's the other way around. Well, anyway, the point with these coordinates maps to the point with these coordinates given by like that. Right, so this is a map of C3, and so if you want to think of the C3 here as a picture, then there is a plane here given by x1 equals 0, and this plane is entirely contracted to the origin, and then outside the origin, nothing happens. It's an isomorphism. It's a sort of scaled isomorphism by, z equals 0. So I take the plane here given by z equals 0, then obviously when z is 0, x and y and z are all 0. So there's a whole plane here, the x1, y1 plane, z equals 0, that's contracted to a point, and then outside that it's an isomorphism. Right? And then, so inside here, I have the surface S1, so here I have the surface S given by, x. So here I have x1, and this is given by, so I take the f, and I write f, x, y, z. This is f of x1. So this is x1 z squared plus x plus y1 z squared plus z squared. Right, and I notice that this is z squared times f1. And the f1 is x1 squared plus y1 squared plus 1. Yeah? And so this x1 here is given by f1 equals 0. And as you can see, this is non-singular. Now I've done something silly, because it doesn't meet the locus z equals 0 anymore. What's happening? So what this is a sort of picture like this. Right? The z doesn't appear here. The z doesn't appear in this equation. So this equation is a cylinder. This is only a local analytic picture. So I replace the thing which is a cone by now this thing which is a cylinder. And of course it's a cylinder over a curve which is not complete curve, because x1 and z1. x1 and y1 there have to be allowed to go to infinity if I want a complete curve. So the complete curve would be x1 squared plus y1 squared plus z squared, and that will be the conic there. Yes? So, it turns out, so there's this, let me write E for the curve given by f1 equals z equals 0. So this E is certainly contained in x1, and it's certainly E is certainly isomorphic to P1. Right, this is one affine piece of it, and it's just the ordinary circle. I mean, in complex coordinates, it's the ordinary circle. Yes, and so at some point I've got to persuade you that E squared is minus 2. Right, so if I take so why is this true? Because take H, general hyperplane, general plane through P and X. In other words, I take this this cone and I just cut it by a plane. Right, then if I do this, let me call this sigma now, sigma upper star of H. This is intersects E in 2 points. Right, maybe H is given by, AX plus BY plus CZ equals 0. And then after blowing up, after the blow up, it's AX1 plus BX1, Y1 plus C equals 0. Right, so it's so there's this curve here in the plane, and I say and a general line, and so this and so there's this. If I do sigma upper star of H is sigma upper star of H is the exceptional curve E itself plus this H primed, and E intersect H primed is 2 points. Right, so you can so E times sigma upper star H is 0, because I could just move the plane at H away under linear equivalence. I can move the plane away from the point, and then it's disjoint. On the other hand, this is E times E plus H primed. This is still 0, and E times H primed is 2. E squared is minus 2. Okay, so this is one way of finding a -2 curve on the surface. Okay, so let me go back to this study that I had earlier. So S is a minimal surface of general type. Right, so I have Ks. Ks squared, Ks is an F, and Ks squared is positive. Right, and so I ask what are the curves C with Kc equals 0. Well, I've already done this calculation for you. I'm going to have first of all the index theorem says each individual. So what are the curves Ci with k times Ci equals 0? Ci squared is negative, right? But then we have this kci equals 0, and Ci squared is negative, and so then if I do k plus Ci times Ci, this is the canonical class of Ci. This is supposed to be degree negative, right? And this means it's -2, right? So then kci is 0 and Ci squared is -2. So in other words, each of these curves, each curve is a -2 curve. Each curve with this property is a -2 curve, and if I do Ci Cj, so if I do the intersection pairing, this is negative definite. Right, so if I take the lattice generated by these curves Ci, so this is Z times all the Ci, all possible Ci contained in the divisor group of S, then Ci squared is -2, and Ci, Cj, and so on give a bilinear form. Thank you. Bilinear form, and the bilinear form is negative definite. Right, it's negative definite by the index theorem. So the index theorem, remember, says that if I do this intersection pairing business, I get plus intersection numbers here, and the canonical class is one of those, and then I'm working in the orthogonal complement of this. So this is k perpendicular. Right? And so all of these curves here have to have, well, when I stated the index theorem, there was all this business about intersection number less than or equal to 0, and if it's equal to 0, then the curves have to be numerically trivial. But none of these curves are numerically trivial. Right? So all these curves are linearly independent in div, in n1 of S. So this is remember, this is divisors of S divided out by numerical equivalence. Okay, so I said, well, we've done one of these. We found one example, and here we have this. So if I have two curves Ci, if I have C1 and C2, for example, then what are the possibilities? I could have C1, C2 is disjoint. So this means they're disjoint, right? If they intersected at all, I'd get a positive thing. If they coincided, I'd get -2. Right? And so if this number is 0, these curves are certainly disjoint. Right? Or C1, C2 equals 1. So this is, you know, the first case was like this, the second case is like this. So what happens if C1, C2 is greater than or equal to 2? Well, it might mean, for example, that the two curves are like this. Okay, so is this possible? So this guy here is, this guy is a contradiction. Right, because C1 plus C2 all squared is, so it's minus 2 plus 2 C1 C2 minus 2. Okay, I'm just calculating the square of this, and minus 2 for C1 squared, and then this cross term. And so if C1, C2 greater than or equal to 2 would give that this guy here is greater than 0. Right? And this contradicts negative definite. So if there are two of these curves, then they have to meet like this. So there is an easy analysis gives that the connected components are, so AN, which is a chain of N. So I'm only interested, at the moment I'm only saying connected components. So if I have disjoint things, I'm not going to worry about it. I'm going to treat all the disjoint guys separately. Right, AN. DN is this picture. Right, so this is not a simple chain. There's a little bit of branching going on here. However, the branching can only take place at the end. Right, n is the number of the curves, so here there are, you know, there's n minus 1 up to there, there's n minus 3 up to there, and then there's 1, 2, 3 final ones. Right, and so this is for n greater than or equal to 4. N equals 3 corresponds to, yes, and then there are E6, E7, E8. Right, so E6 is like this, 1, 2, 3, 4, 5, and I have branching like that. So, you know, in this case there's a little bit of branching going on. Right, and a little bit of branching is not at the penultimate stage. Right, but it's not far off it. Right, and then E7 is the same, but one more. Okay, so I hope, so I'll draw these as Dynkin diagrams in a minute, but I hope you can see what the picture means. This means, this last picture, there are 8 curves. Any two curves there are either disjoint or they meet transversely in one point. Right? This is basically a simple chain, except I'm allowed one branch point. And the branch point in each of these cases must either be right at the very end of the chain or just one step in from the very end of the chain. And moreover, I'm only allowed to have 6, 7, or 8. Okay, so these pictures, this analysis, the lattice corresponding to this, appears in many, many different branches of mathematics. This is sort of one of these, this is a sporadic, a case of sporadic combinatorics, but they appear absolutely everywhere. They appear in group theory or in Lie algebras or in singularity theory or in lots and lots of places. So, you know, this is a huge area of mathematical culture. Let me try and set out some of the numbers. So AN looks like this, with n nodes, and a dn, sort of basically the same picture until I get close to the end, and then right, so now here again the n nodes, there are always n nodes, E6, is, so, you know, it's easy to draw this. You draw 5 dots in a row, and then you join it with a guy up there. E7. I draw 6 dots in a row. I join it like this, and E8. It's the same, exactly the same picture, except one more at the end. Okay. So what these? So if I the most primitive place where these pictures occur is I take a quadratic form and a bilinear form. So I take a Z module L lattice, a free Z module, and I have a form on it. I have a bilinear form, and in my case I want it to be negative definite, but if you said positive definite it would just be the same, negative definite, generated by -2 vectors, and I want it not, so indecomposable, not a direct sum of 2 sublattices. Okay, then so the thing I'm saying here is let's have a Z module generated by -2 vectors, and it's got a quadratic form on it, and then it has some special property. So its special property is that this is negative definite, and also it's not a direct sum. Right? Then this, if I've got any such lattice, and I choose a basis, and I choose the generating elements as stated of -2 curves, then I get one of those pictures. Okay, so why can't I have C1, C2 with C1 squared, C2 squared equals -2, and C1, C2 equals 2, for example. Why can't I have that? Right? Well, that's just exactly the argument I gave you over there. Right? Because C1 plus C2 squared would be positive. Right? And that contradicts negative definite. So why can't I have, for example, this picture? Or more generally, why can't I have this picture AN together with a why can't I have any cycle? And the reason is, suppose I had, you know, C0 plus C1 plus C2 plus Cn with these forming a cycle like this, and then the last one going back to there. So that's this picture I'm drawing here, C0. Right? Well, just do the same calculation. I'm going to write down C0 plus C1 plus C2 plus Cn, all squared. Right, and what do I get? Well, you know, I'm going to do the intersection Ci squared, right, is -2 there. So I get n times -2.
N plus 1.
Yeah, thank you. N plus 1 times -2. And then I'm going to get twice C0 C1, because I'm assuming these guys are linked like this. I'm assuming that C0 and C1 are joined. So when I calculate the square here, I get C0 squared times C1 squared is 2. And C1 squared, C1 C2 is 2. and so on all the way around. And Cn C naught is Cn C naught is 2. Right, so you do this calculation, you get 0 again. But basically, it's the same as this calculation. It's longer to say and to write down, but it's the same calculation as here. Right? So you know, what properties characterize these graphs? Well, you'll notice that I can have 3 vertices coming out of a point, but I can't have this. Right? Why not? Well, it's basically the same reason. If this is E0, E1, E2, E3, E4, right, then write down 2 E0 plus E1 plus E2 plus E3 plus E4. Right, and calculate this squared. And you'll find out that this is 0. Right, so why is this? So this is minus 8, minus 2, minus 2, minus 2, minus 2, and then plus, well, it's 4 E0 E1, plus 4 of that, E0 E2, E0 E3, and that's all 0. Right, I've got minus 16 coming from there, and I've got plus 16 coming from there. Right, and then why can't you have? So this says there can only be. This says you can only have 3. So in these diagrams there can be branching. It's not true that each of these diagrams is just a chain, but you can only have a certain restricted amount of branching. So you'll notice that in each of these pictures there's only 1 branch point. Why can't you have 2 branch points? Why can't you have this? Or why can't you have, why not something like this, where the branching is not right close to the end? Well, it's the same reason, right? Give these 1, 1, 2, 2, 2, 2, 1, 1, calculate the square, and you'll get exactly the same answer as here. You'll get this vector here has square 0. So I'm saying these the restrictions on these diagrams. First of all, each of the guys has minus 2, and any 2 guys either meet in 1 or meet in 0. Then no loops. Then only 1 branch point. And then the branch point must be either right at the end, or it has to be that near the end, and the tree is only like this. So why doesn't this one work? Well, if you think about putting 4, 3, 2, 1, 3, 2, 1, 2 there, you will find that you'll get something. So, this picture is a little bit special. So let me just analyze this one. So, these 7 vectors I've written down here are called E0, E1, E2, E3, E4, E5, E6, E7, and you can choose how you name them. Right? You can write down this calculation and do it for yourself. Right? However, I'm going to take this combination of the vectors. Then I say, I take this combination of vectors and I multiply it with any EI, then I get 0. So it's not true just that the whole product is 0, but the whole product is this combination multiplied by any one of the vectors in it is 0. So for example, if I try it in this middle one, that seems the most suspicious. I'm getting whatever this one's called, let's call him E. E times the whole cycle is, well, it's minus 8 coming from his self-intersection. Minus 2 times 4 is minus 8. And then he's plus 2 plus 3 plus 3, and that's 0. Yeah? And so in the same way, I'm not allowed to extend that diagram this way. Right? I'm not allowed to, and so on and so forth. I'm not allowed a 9th step there. So you can do all of these are given as exercises in these notes of mine. Okay, so do these really happen? So this is a big subject, and I've studied them over my whole career and so on. Lots and lots of other people have done. So it's a big subject. So the corresponding singularities. So they're all hypersurface singularities, hypersurface double points. So they're given by f equals 0 in C3, and the f is up to analytic equivalence. I'm not really going to spend too much time telling you how to do the analytic equivalence concern, but it's x squared plus y squared plus z to the power of n plus 1. This is called an. Now, x squared plus y squared plus y z to the n, x squared plus y squared z plus z to the n minus 1, this is called dn. And then x squared plus y cubed plus z to the fourth is called d6. X squared plus y cubed plus y z cubed is called d7. And x squared plus y cubed plus z to the fifth is called e8. Right, so these are called the Duval singularities. So let me explain how to explain that these, at least try to give some examples to see that these singularities have a resolution with the graph of exceptional curves that I drew over there, that I'm just rubbing out in these cases. So we did the case I did is A1. So if you look at A1, it's the ordinary double point, and it blows up to give exactly 1 minus 1 curve. Right? So for example, if I do x squared plus y cubed plus z cubed, right? So this is D4, right? This is, so if you put n equals 4 here, you get x squared plus y squared z plus z cubed. So this y squared z plus z cubed is a cubic form with 3 distinct roots. So up to, I'm just changing coordinates a little bit in the y and the z line. Right? So what do I have to do here? I say that, so this is x in C3 is like this. Right? Let me do the blow up exactly as before. So this is x1 in C3 1. And I'm just going to write x equals x1 z and y equals y1 z, and z equals z. Right, so this x1 here is given by the equation f1 equals 0. Right, and who is f1? Well, I'm going to do x1z squared. I'm just writing down this polynomial here in these variables. It's x1z all squared plus y1z all cubed plus z cubed. Right, and now I'm going to take out z squared. I'm taking out z squared because this point is a hypersurface double point. It's a double point, so everything in the maximum ideal, so this thing here is contained in the maximum ideal squared. So I can always take out anything in the maximum ideal squared after doing this. Right? So who is this? This is x1 squared plus. So I hope I'm doing this right. This was cubed, isn't it? So this looks like y1 cubed z plus z. So you know, I should draw a picture of the C3. So the C3 looks sort of something like this. In it there's a plane z equals 0 that's getting contracted to the point, and this plane is of course C2 with coordinates x1, y1. So I want to see this as y1 cubed plus 1 times z. You see where it's singular?
Must be. Yeah, if you take this derivative with respect to z, you obtain y1 cubed plus 1.
Yes? So what's this? This is 3 points on the curve z equals 0. So you know, here there's some curve, and on it, right? So you know, I've got some in the picture I had before. You know, we were sort of lucky. We got a resolution of singularities after just one go. So I've got some surface there, sitting in this new ambient space. I can cut it with z equals 0. If I cut it with z equals 0, what do I see? I see x1 squared. So in other words, this surface here is tangent to the plane z equals 0. In other words, I take z there, I take the original z, I lift him up to c1 cubed. I take the maximal ideal of the origin here. I lift him up there, and it vanishes twice on this curve. So z vanishes twice on the exceptional curve x1 equals z equals 0. It's the y-axis. Geometrically speaking, in C3, it's just the y-axis, the y1 axis, right? But the thing vanishes twice on it, and x1 has 3 ordinary double points. Right, so you know, you will eventually find out, if you care, that if you blow up these 3 ordinary double points, you get a new exceptional curve that meets the first exceptional curve. So this is the first blow up, and then this is what happens if you blow up these 3 subsidiary nodes. Right, and this is the Dynkin diagram D4. Right, and you can also check that Ci squared is -2. And CICJ is as drawn. It's 0 or 1, depending on how I drew it. Yes? So, you know, resolving the other singularities is a really interesting example. So, you know, you can go to my website and download this paper. At the end of this chapter, there are a little sequence of 20 examples to work out. And so, you know, those pictures, those graphs and so on are there. Right? And all of these calculations are fun. They're basically, you know, I don't say they're very easy, but they're fun. And so, and you learn a lot by doing them. So you have to do, you know, if you're going to be a grown-up algebraic geometrist, you have to do these calculations. Okay, so I'm basically just giving a list here of things, and you know, you can also make a list. This is also a strange fact. So these singularities are also quotient singularities. By finite subgroups in SL2C. So let me just give one or two examples of this, because you need notation and so on, and basically some sort of clumsy matrices. If I take epsilon is exp of 2 pi I over r, right? So this is a primitive rth root of 1, right? Then I can take the matrix 0, 0, epsilon to minus 1, right? And I think you'll agree that this belongs to SL2Z. SL2C, I'm sorry. Yeah? And so this is the group action here is xy maps to epsilon x, epsilon to minus 1y. Right? So this is an action of the cyclic group Z mod R acts on C2. So quotient singularity. So quotient, you can think of this same Z mod R as acting on the polynomial ring C of xy. Right, so when I've got a group acting on a field, then it's a good idea to think about the field of invariant functions. So this is the thing that gives you Galois theory. You take the fixed field of a group action. So I'm going to do the same thing here. So what is the subring of invariance? Right? And so, I'm sure some of you already know the answer, and you can also just calculate it. So, obviously, x to the power of r is invariant, because if I multiply this x gets multiplied by epsilon. If I do x to the power of r, then it gets multiplied by epsilon to the power of r, and that's 1. Right? And similarly, y to the power of r, and then, well, xy. Right? So xy means the product xy gets multiplied by 1. It gets multiplied by epsilon to minus 1, which is 1. Right? And you can, it's true that c xy invariant under Z mod R is equal to the ring generated by these three guys. Right? And so this is a ring that needs 3 generators. And so if I call the generators U, V, and W, then you'll notice that they satisfy the equation UV equals W to the power of R. Right? And so this is isomorphic to polynomial ring variables U, V, W divided by equation U, V equals W to the power of R. Yes? And this is this singularity here, right, with R is n plus 1. So this is type A, R minus 1. Okay? And, it so happens, this is a miracle. It was discovered by Felix Klein around 1870, and by Duval and Coxeter around 1930, that, I've given 3 different lists here. I've given these lists of ways of generating a very special kind of lattice, a lattice with very special properties. Here's a list of singularities. So this is just a list. I'm not characterizing them, although they do have very many different characterizations. Right? And then we have this other strange thing that I can look at subgroups of SL2C. So subgroups of SL2C the cyclic one is the obvious one. There is also something called the binary dihedral group, and then afterwards there's the binary groups corresponding to the Platonic solids. So the Platonic solids are things like the icosahedron. If you take the icosahedron, that has a group of symmetries. Icosahedron has, I think, 60 symmetries, right? That's a group in SO3. SO3, orthogonal motions of 3 space. That's the one you can see. Take a football. It has a, the old footballs had dodecahedron, had 12 5-sided, 12 pentagons as their face. You can turn that around in 60 different ways, right? That's a group in SO3. And so there's a way of seeing SU2C as the double covering of SO3. And you get binary. Anyway, all of this stuff is actually listed in this paper. And so, maybe you can think about reading this. So I want this for quite specific reasons. So I said, these bunches of curves, these bunches of -2 curves, they appear on algebraic surfaces of general type as the orthogonal complement to the canonical class. Right? So I have an algebraic surface here. I have an algebraic surface here, S. I've got this Ks is an F, and Ks squared is big. And I would like Ks to be ample. Right? And Ks times C equals 0 contradicts this. And so I want to take all these curves, all these finitely many curves, and I want to get rid of them, but in this case I want to contract them. So I do S maps to X. So this has these curves on it, and this one has these singular points on it. Right? And this one, so this is a little bit singular. It's not exactly the category that I started working with, but on the other hand here, Kx is defined and is ample. Right, and so it's here that we can actually talk about having very ample. Having, for example, 5K is very ample. So this is the right place to state these theorems of Bombieri, which is my immediate aim. So please go to my website and download this paper and do some of the exercises in it. I find this actually also the last chapter of Shafarevich. If you look at Shafarevich, Basic Algebraic Geometry, the first book, chapter 4, then it has a lot of the same exercises in. It has them in because I translated the book. Okay. So I'm lecturing on Wednesday and then next Monday, and then after that we're having a holiday. Any problems? Anybody want to discuss this material? Anybody want me to set some homework?